So welcome back, everyone. We're going to continue talking about minimum spanning trees today. So in the previous lecture, we saw Kruskal's algorithm, which was this global greedy algorithm for constructing minimum spanning trees of finite graphs. So by globally greedy, I mean it always sort of chooses the smallest weight edge among all of the possible allowable edges to add. And today we'll focus on a local procedure for building minimum spanning trees called Prim's algorithm. The definition is fairly straightforward. We'll check that it indeed builds minimum spanning trees on finite graphs. Then we'll start to think about what happens when either or both algorithms are applied in the setting of infinite graphs. Okay, great. So let's get started. So I'll just jump right into defining Prim's algorithm. So here the input I'll assume is a connected graph. With a vector of weights W, as before. And this time we need additionally some starting vertex, because we're going to proceed, locally growing a tree from a single node. We need somewhere to start. So we call the starting vertex rho, and we'll define Prim's algorithm by just saying what edges are added by Prim's algorithm as it grows. So initially there are no edges and just one vertex, which is this starting root vertex rho. And then so for each I non-negative integer I less than the number of vertices, we take the smallest weight edge, connecting all the vertices we've added so far to the rest of the graph. So EI is the minimum weight edge from V naught up to VI minus 1 to the rest of G. And then so that will be the newly added vertex. So if I write, say, EI as having endpoints UV, then we'll write VI to be V, and this is where, so we're assuming that the first endpoint was already part of the set that we've grown, and so V is the new guy. It's not in the set of previously explored vertices. Okay, and then we add this new edge to the growing edge set. So this is EI is EI minus 1 union this new edge, little ei. Okay, and the output then is just the graph with edges E, so the final edge set, E sub V. Maybe it's V minus V minus 1, except, okay, so that's so that procedure I hope is fairly clear. So at any given time, you've built some tree with vertices, so V naught, V1 up to VI minus 1, and then because the new edge that's added always goes from some previously explored vertex to some new vertex, VI, that's sitting out in the rest of the graph that's built always has to be a tree. You can't create any cycles. Okay, but I'd like to note that this procedure sort of immediately makes sense, even if the graph we start with is infinite under some sort of mild conditions. So this process makes sense even if the vertex set is infinite, as long as we can make sense of our choice of the smallest edge leaving a set at any step. So a sufficient condition for that is that for any positive C, if I write, let's say, EC for the set of edges of weight less than C, then that gives me a graph. So the graph with edge set EC has finite degrees. Okay, right. So that's just saying if we, you know, if the way to think about this is if we've, so I'm imagining now that I might be sitting in some infinite graph, but at any step I of the process, I've grown some finite tree, and now if I sort of look at the edge boundary of this tree and gradually raise the weight, asking what's the smallest weight edge that I see, that boundary will start with no vertices, and then at some point it'll go up to one vertex, and I'll take, or no edges, and at some point it'll go up to one edge, and I'll take that edge. Okay, it won't suddenly jump to infinitely many edges, or it won't instantly be infinite for any positive C. Okay, so this condition that if I restrict to edges of any finite weight, I only see bounded degrees is enough for this algorithm to be well defined even on infinite graphs. Okay, so so graphs like this we'll call these locally finite. Okay, so so I hope that that makes sense. So the next thing that I'd like to do is show that this procedure really does output a minimum spanning tree, at least on finite graphs. So if G is finite, then the output of Prim is an MST. Okay, and so here I'm using an MST, so I'm allowing sort of multiple edge weights to be equal. So let me just comment that, you know, at this step of the algorithm, where we choose the minimum weight edge from the edge boundary of whatever we've built so far, we can make that choice arbitrarily. So if the edges are all distinct, it's the unique minimum weight edge, but generically it can just be any minimum weight edge. Okay. So so to prove that Prim's algorithm will always output an MST, I'm just going to show inductively that at any given stage, the set of edges that we've added is the edge set of is a subset of the edge set of some MST. Okay, so so what we're going to show inductively is that for all I, the set EI is contained in the edge set of some minimum spanning tree. Okay, well, the base case is trivial. The empty set is contained in the edge set of every minimum spanning tree. Okay, and then for positive I, so we'll be supposing that, you know, E1 up to EI minus 1 are all edges of some MST. Let's give it a name, so let's call it T. Okay, one such MST. And now I'll write, so remember EI is the edge added at step I. It was UV, where V is not in, V is the far endpoint. V is not in the previously added vertices, right? So V is the new vertex VI that's added, okay? And so let's think about, let me draw a picture of that. so you know, we've grown some tree up to step I minus 1, so that's what's over here, the edges E1 up to EI minus 1. And now we add this edge EI into the graph at step I. Okay, so there it is. And now I want to think about the path between the endpoints of this ith edge in the tree T. Okay, so let's let gamma be the UV path in T. Okay, so there's two possibilities. Maybe gamma is actually just the edge UV. This is an edge of T, and that's great. Then we're done, because all we're trying to do is show that that when we add in EI, the edge set, this enlarged edge set is still the edge set of some minimum spanning tree. So if this is an edge of T, then that does it for us. So if EI is in gamma, or in that case it's equal to gamma, then EI is in T, and that's great. Okay, and otherwise, let's think about what the path gamma does if not, right? Then the path gamma has to connect U and V in some other way. Maybe, you know, it goes over here and then out of the tree somehow and comes back to V, right? But then there's another edge, right, over here that leaves the tree and is an edge of gamma, right? So otherwise, there's an edge E of gamma, which connects. So the first vertices, V naught up to Vi minus 1, to the rest of the graph. Right? But EI was a minimum weight edge connecting these vertices to the rest of the graph. And so this edge E must have weight at least as big as EI, right? So then by the definition of EI, we know that the weight of E is at least the weight of EI. Okay, and so then we can do a swap like we did in you know, our analysis of Kruskal's algorithm. We'll just take the tree. So you know, this blue path here is all contained in the tree T at this point, right? And so if we swap the edge E for the edge EI, we get another minimum spanning tree, right? Or another spanning tree. Okay, so then the tree T prime, which is T minus E plus EI, is another spanning tree. And its weight, right, is the weight of T minus the weight of E plus the weight of EI, which is, you know, because we said the weight of EI is at most the weight of E, this is at most the weight of the tree T. And so that means that T prime is another minimum spanning tree. And so we've, in that case, constructed a minimum spanning tree which contains all of the edges up to EI minus 1 and additionally EI, right? Okay, so that completes the inductive step, showing that there's an MST that contains all of E1 up to EI. Okay, so that proves that on finite graphs, Prim's algorithm builds a minimum spanning tree. Okay, and you know, it's also a fairly natural procedure. You can ask the same question: how generally do sort of local greedy algorithms yield minimum spanning structures? And there is research on that, but the answer isn't as clean as it is for matroids, and it takes us. It also doesn't lead to like that digression into matroids allowed me to introduce the dual, and that was cycle breaking, which is useful to us. There's no, if we investigated the generality of Prim's algorithm, it would really be a full digression from the course. I'm not going to go into that, but I might put some references in the notes if I have time. Okay, so so where I really want to go now is to think about both of these algorithms, Kruskal's algorithm and Prim's algorithm, in the setting of infinite graphs. So any questions about the proof of correctness before we go there? Okay, so let me continue. Okay, so Kruskal's algorithm has big problems on infinite graphs. I mean, at least naively. Okay, so it doesn't formally make sense. Because, you know, it starts by ordering the edges and picking the first one, right? So, you know, if our graph, if what we started with, for example, was the lattice Z2 with IID uniform edge weights, right? Then Kruskal's algorithm can't even get started. There's no first edge. Okay. And you know, you could impose some local, some condition like we did for Prim, where we said, okay, well, there's only boundedly many edges of less than any given weight, but that's imposing that globally is quite a restrictive condition. It doesn't lead to sort of particularly natural classes of graphs for which you can say nice things. Okay, so instead of taking that approach, another thing you can do is try to just continuize the process in the same way that, you know, we had a discrete version of the Erdős-Rényi process where we added the edges one at a time, and a continuous version where we had a parameter p which we could vary continuously and watch the edges appear. We can sort of try to do the same thing with Kruskal's algorithm. Okay, so that's one. I'm writing solution, but it's just one possible way to try to get a good definition of a variant of Kruskal's algorithm in the infinite setting. So we could, you know, if we're given our graph, our weighted graph, which now might be infinite, and some positive t, let's write, you know, ET for the set of edges. I think I already used this notation earlier when I was talking about locally finite graphs for a Prim, right? So ET is a set of edges of weight at most t, and I'll write ET minus for the set of edges of weight less than t. Okay, and now I can, if I write GT for the graph with edge set ET, and you know, GT minus for the graph with edge set ET minus, then I can try to define a, what would Kruskal's algorithm say if we imagine continuously varying the parameter just before time t? This is the graph we have, right? And then if we're going to add an edge that has weight exactly t, we would only want to do that if it joined distinct components of the graph that we had just before, right? That's what Kruskal's algorithm did. It just did it in discrete steps rather than continuous steps. Okay, so that's one natural way to define a sort of spanning forest procedure. Okay, so which generalizes Kruskal. So we'll define what's called the free minimal spanning forest. So this is so the subgraph of G, whose edge set is just what I just said in words. So it's the set of edges UV of E such that U and V are in distinct connected components at, you know, just before the edge UV is added. So of the graph G of this process at time WE minus. Okay, so now, so this is just the, if you look at the, so this is a perfectly fine definition. You can imagine this as being the outcome of the process of a process which varies in t, and at any given time adds an edge that if at that moment it would join two distinct connected components of the coupled graph process, just like in Kruskal's algorithm. Okay, and I'll leave you with something to think about in this definition. Which is to show that the free minimum spanning forest may not be connected. Okay, but it is acyclic if all the edge weights are distinct. Okay, and by the end of, I'll be giving some. We'll be defining a second notion of minimum spanning forest in a second. This exercise sort of gives a bit of justification for the fact that I'm calling the outcome a forest and not a tree. But we'll see examples. We'll see some sort of counterexample examples over the course of the lecture, which might give you a bit of sort of hints as to how to approach this one as well. Okay, so that's a first attempt at kind of defining an analog of Kruskal's algorithm. Well, it's the only analog we'll define on infinite graphs. But I also want to think a little bit about how Prim's algorithm behaves on infinite graphs. Even though we said it was well defined, that doesn't mean that what it builds is going to be something that we like or find useful. So I want to sort of talk about the caveats there and what we can say. And so there's one sort of big issue with Prim, which is that its locality means that it might not even explore the whole graph. Okay, before I say that, let me note that on infinite graphs, so Prim is sometimes called invasion percolation. Which in some way I prefer as a name because I'm generally, my preference is to give things names that describe what they do more than name them after people. And in this case, I think that Prim wasn't even the first person to come up with Prim's algorithm. I think it was a guy named Jarnic. So there's, maybe invasion percolation is a better name. But okay, so whatever you call it, it might not build a tree, or it might not build a spanning tree. And so a very simple example where it doesn't is just, consider the line where the edge weights are dyadic. So like 1, 1/2, 1/4, 1/8, 2, 4, 8, 16. Right? So here, no matter where I start Prim's algorithm, it always adds the smallest weight edge that connects what I've grown so far with the rest, right? So it'll just always the edges get smaller to the right. So Prim's algorithm will always just grow to the right, and it'll completely ignore the left half of the line wherever relative to wherever it starts, right? So that's a sort of potentially serious issue. Is it just doesn't even consider big parts of the graph, right? And if these edges, there could even be, if I start here, there could even be small weight edges far over to the left that the process will never see just because there's a large weight edge that blocks them. Okay, so so one way to get around that sort of issue, that the algorithm just doesn't explore everything, is just to say, well, let's just run it from everywhere and then look at what we get if we run it from everywhere. Okay, so that's a sort of very naive but reasonable solution to the issue. And it gives us another notion of spanning forests. So again, if we're given locally finite graph, okay, then the wired minimum spanning forest, it's called, is the graph with, so edges given by the union over all starting locations for Prim's algorithm of the edges of T row. Remember, we'd written T row for the output of Prim's algorithm starting from vertex row, right? And so now I'm just taking the union of all of those edge sets. Okay, so so this also might not be a tree. At least now it does explore near every vertex, right? Every vertex is guaranteed to be connected by some edge into something, because the algorithm does an infinite exploration starting from every vertex. But let's look at an example to see that it doesn't have to be a tree that comes out the other side. So here's a picture, right? So let's think about what happens on this graph. Okay, so the setup here is that, so if you imagine this is like, so it's a ladder, you know, starting in the middle here, going to the right along the top, the edge weights are getting smaller. Starting on the bottom here, the edge weights, maybe I wanted this to be, I think this is fine. Yeah, the edge weights here are getting bigger, but they're all smaller than any of the sort of boundary of this region, right? The edges along here are all smaller than these 0.5s and this 0.3. Okay, and then the edges are getting sort of bigger over to the left and bigger over to the left, but again, they're all smaller than any of the edge weights that show up in the middle here. Okay, so what's Prim's algorithm going to do? Well, if it starts on the top, it'll just explore to the right, like on the line that we saw before, because all the edge weights to the left are bigger and all the edge weights going down are bigger. Okay, if you explore on the bottom, likewise, you'll just explore to the right. The weights go down for a bit, then they go up for a bit, but the sort of boundary consisting of vertical edges plus the edge to the left always consists of edge weights that are bigger than anything to the right. Okay, and so that means that for this graph, you know, the wired minimum spanning forest, so I'm going to use WMSF, consists of all horizontal edges. Okay. What about the free minimum spanning forest? So remember, this is the graph we get where we add an edge if it joins distinct connected components of the graph you get by only looking at strictly lower edge weights. So what are the edges of that here? Well, you know, if we're increasing the threshold, the edge threshold, until we get to vertical edges, there's no way to make a cycle because we'll just be adding edges on the lines. So we'll add all the edges on the lines, okay, all the horizontal edges. But then at 0.5, we'll also add this vertical edge, right? Because at that point, we'll have these two infinite lines disconnected, and adding this edge doesn't create a cycle, right? So we'll additionally add this this edge 0.5 in that case. Okay, so the free minimum standing forest contains all horizontal edges plus the edge of weight 0.5. Okay, so that in particular, and after that, once you increase the edge weight above 0.5, well, we've already built at that point a spanning tree of the graph, right? It touches all the vertices, so we're not going to add any more edges. Any additional edge that was added would create a cycle. Okay. So there's a question in the chat that I don't think I'll try to answer. Is there a version of Prim where you do more than omega steps? Maybe there's a problem with the smallest weight edge after infinitely many steps. Yeah, I don't think I'm going to be able to say anything intelligent about that on the fly. Sounds interesting. Okay, so I'd like to, this example shows that the free minimum spanning forest and the wired minimum spanning forest somehow can be different from one another. Okay, the term wired, by the way, somehow corresponds. There's one way to think about the wired minimum spanning forest is to imagine that all the infinite paths sort of join up at infinity, and so you could sort of route through infinity to create a path between different places. So in that picture, once you create the infinite horizontal lines, then you actually already have a connected graph if you've kind of compactified your graph by adding a connection at infinity. And so, or wiring everything together at infinity. So that's one way to think about where the name comes from. Right. So I'd like to now prove a sort of characterization of the wired minimum spanning forest, which has more of the flavor of the one given for the free minimum spanning forest, right? So the free minimum spanning forest, we said that we add an edge if its endpoints are in distinct connected components, sort of at the time just before. And now for the wired minimum spanning forest, so almost the same is true. It can't be literally the same because we've seen that the two graphs can be different. But so if we're given an infinite and locally finite graph with all edge weights distinct, okay, then so for any edge E of the graph, E is an edge of the wired minimum spanning forest if and only if so U and V are in distinct components of the graph. So they have to be in distinct components at the time just before the weight of E. But now additionally, we require that at most one of them, of those components, is infinite. Okay, so this is a equivalent characterization of which edges are in the wired minimum spanning forest. It's sort of non-algorithmic, if you like, whereas before our definition just involved running Prim's algorithm and seeing what we get. Okay, it also shows that the wired minimum spanning forest is always a subgraph of the free minimum spanning forest because our condition for being an edge is more restrictive. Okay. So let's prove that that this characterization is correct. So I'll throughout the proof I'm going to write. So I'll try to make them look like C's and not like E's, but if they look like E's, then know that they're really C's. So I'm going to write CU and CV for the components of U and V, respectively, in this graph GWE minus. So let me, you know, I'll need a couple different drawings of those depending on whether they're finite or infinite and things. You know, I'll try to make this rather visual proof because I think it's the easiest way to understand what's going on. So I'll prove the sort of reverse implication first. So that's to say, if at most one of these components is infinite, and they're distinct components, then this edge is in the wired MSF. Okay, so let's suppose, I mean, if at most one of them is infinite, then at least one of them is finite. So without loss of generality, we can say that that's CU. So let's suppose that CU is finite. Right. So here it's here's the component. Here's my sort of blob representing CU. Okay. So what's the structure here, right? This is a component in this graph which only has edges of weight less than E, less than WE. Okay, so that means all the edges in here have weights less than WE, and all the edges leaving this for the rest of the world have weights greater than WE, except for the edge WE itself, right, which has weight exactly WE and connects, maybe I should draw my vertex U down the bottom, connects U to the vertex V somewhere over here. Okay, and so what's Prim's algorithm going to do? Well, the algorithm always explores the smallest weight edge available to it. So that means it's going to exhaust all of the edges of weight less than WE before it ever investigates any edge on the boundary, right? So then, so Prim's algorithm, it'll first build a minimum spanning tree of CU, right? And then once it's done that, then it has no more edges of weight less than WE available to it. It adds the smallest weight edge which is available to it, which is this edge UV. So then it adds UV. Okay, and so that means that UV is an edge of the wired minimum spanning forest. Do I mean the free minimum spanning forest? The wired one is the one that Prim builds. Okay. Right. So Prim's algorithm. Yes, I should have said the confusion was reasonable because I didn't say where I was starting. So started from U. Okay, so I'm imagining starting the growth process from something, U or indeed anything in the component of U here. Then it'll first exhaust all of the edges of weight less than E available to it locally. And when it's done so, it'll be forced to add this edge UV. Okay, is that part of the proof now? Okay. So that sort of was quite, that direction is easier. For the other direction, we need to think a little bit more. Neither direction is particularly hard. So for the other direction, I'm just going to show that, so what we showed here is that if at least one of the components is finite, then this edge UV will be added. So now I just want to show that if both components are infinite, then this edge UV won't be added. Okay, so here I'm supposing that CU and CV are both infinite. And I think I have a picture to help me with that. I'll use this one. Right, so now I have to show that no matter where, remember the wired minimum spanning forest has the edges that Prim's algorithm adds no matter where it starts. So what I have to prove, so I want to show that UV is not in the wired minimum spanning forest. I have to show that no matter where you start Prim's algorithm, it's not going to add this edge UV. Okay. So we'll sort of take that in a few steps. So if so we're looking at Prim run from a vertex row. Okay, so easy cases are if row is, if we start from the vertex U, right, then what do we know? This is so this component over here, CU, is infinite. That means that there's infinitely many edges connected to U which have weight less than WE. Okay? And Prim, always being greedy, choosing the smallest weight edge available, will always choose one of those edges of weight less than WE, so it'll never have a reason to add the edge UV. Okay, so yeah, E is UV, right? So then Prim only explores within CU, and so never adds UV, right? And similarly, if we start Prim's algorithm from vertex V, well, then we have infinitely many edges to explore of weight less than weight of UV, and so we never explore the edge of weight UV. Similarly, if row is V, then we never add the edge UV. Right? And so now we need to think about what happens if we start from some other vertex other than U and V. Right? So then let's look at, let's list the vertices explored by Prim's algorithm. Like we did in the algorithm. So that was like V0, V1, and so on, right? And let's look, so there's two possibilities. Either this exploration, Prim's algorithm, now started over at some vertex X. Maybe it never gets to either of these components, and then it obviously can't add this edge. Or maybe at some point it does visit one of these components, right? So, so if I write N for the first time so the first K such that Vk is in one of Cu or Cv, right? Then, so if N is infinite, then, then the edge UV is not in Tx, right? Because that says that the exploration just wanders off in other directions, doesn't go over here, okay? And if N is 0, right, then that means we start in one of the components Cu or Cv, but then, as someone has just pointed out in the chat, in that case, we're always going to have edges of weight strictly less than the weight of E to explore. So we'll never add this edge UV, right? So then X is in Cu union Cv. So we never add UV. Okay, and so now we just need to think about what happens if the process, if N is some positive finite value, right? That means that Prim's algorithm started from X, goes along exploring, it maybe explores a couple of finite components of the graph, and then at some point it adds an edge from somewhere into one of the components Cu or Cv, right? Well then, so let's say, right, that edge, well, so that edge, that happens at time n. So this is, the edge un vn, right? And this was, so this is, this edge is not an edge of this graph, right? yeah, so because I've drawn these these blobs are the connected components of this graph. And I'm looking at it the first time we enter one of these connected components. Okay, so this edge is not an edge of the graph GWE minus, right? So UN VN is not an edge of GWE minus, and so its weight is at least WE minus, but it's not this edge either, and all the edge weights are distinct, right? So that means that the weight of UN VN is bigger than the weight of E. Okay. But what does that tell us? Well, Prim's algorithm always adds the smallest weight edge available to it, right? So at this moment, when we added this edge, the smallest weight edge available had weight bigger than the weight of E. So that means the whole edge boundary of what we'd explored up to time n had weight bigger than the weight of E. But now, after this step, we find ourselves in a component with infinitely many places to explore with weight less than weight of E. Okay, so now we can just explore forever edges of weight less than weight of E, and we never have to touch this edge UV. Okay, so so just to write that down, you know, Vn is in an infinite connective component of G weight of E minus. Okay, and so so all further edges added have weight less than WE. Okay, and so so E is not in TX again. So no matter where we start the exploration, this edge will, Prim's algorithm will not add the edge UV, and that's precisely what we wanted to show, right? The wired MSF is just the union of all these trees built by Prim's algorithm, and we showed that when these components are both infinite, then the edge between them will not be added. Little typo, then UNVN is not in. Thank you. Thanks. Okay. So could you have looked at the first time you reach U or V rather than their components? It's not guaranteed that I'll reach U or V, even if I reach one of their components, right? I suppose that would only help. Maybe that would work. But no, I think it's better to look at the first time you reach their components, because the first time I reach them might be by an edge of weight less than the weight of the edge UV. But it's not. But you know, the first time I enter the component, it has to be via an edge of weight greater than UV. So I think it's better this way. Okay, so so what did we just show? We showed that the edge set of the wired minimum spanning forest consists of edges that, when they arrive in the graph process, you know, connect two components, at most one of which is infinite. Okay, and for the free minimum spanning forest, it was just edges that, when they arrive in the graph process, connect two distinct components without any constraint on their finiteness or infiniteness, right? But now, so we can just sort of use that to get a condition for when these two definitions are equal. So we'll say that a locally finite graph has unique infinite components. I guess I was requiring with distinct edge weights. And I'll abbreviate that UIC and not U infinity C. If for any positive t, the graph GT minus has at most one infinite connective component. Okay, and so the proposition tells us that, I guess this is still within the corollary, if G has unique infinite components, then the free minimum spanning forest is the same as the wired minimum spanning forest. Let me make that of G. Right? Because in that case, every time an edge connects two distinct connected components of the graph GT minus, automatically, and most one of them is infinite. And so it's added to both the free and the wired minimum spanning forest. Okay. And this also implies that, you know, if G has unique infinite components, then all components of the free minimum spanning forest are infinite. Okay, in the wired forest, which is built by Prim's algorithm, all the components are infinite automatically because if you start with an infinite graph, because that's how the process works. You just keep on adding edges forever. You know, starting from every vertex, you build an infinite component. Okay, but in the free forest, you can imagine that some components may stay finite. They may sort of get blocked in every direction by components that, like where an edge addition would somehow create a cycle. Okay, so I mean, you have to think about that, but you know, this may fail without UIC. Okay. But you know, we're now going to focus on the setting of percolation, where the edge weights are going to be IID uniform random variables, so automatically all distinct. And for the most part, I think exclusively actually, we'll be looking at settings where the graph has unique infinite components. So it doesn't matter whether we talk about the free or the wired minimum spanning forests. We can just say minimum spanning forest and there's no ambiguity because the underlying sort of setting will guarantee that the definitions are equivalent. Okay, so so for the rest of the lecture, I'm going to focus on minimum spanning forests and percolation. So my setting is that the graph we're considering is going to be the integer lattice ZD for some D, and the edge weights will be, so with nearest neighbor edges, that these edge weights are IID uniform 0, 1. Okay, so so in this setting, there's so there, I'm going to start with the theorem, and then I don't think I'm going to get to the proof today. I'll probably prove it to you tomorrow. The theorem is about what happens in 2 dimensions. Okay, and I want to talk a little bit about the connection between minimum spanners and percolations in general dimensions, but then we'll come back at the end and exploit some of the sort of special structure of planar percolation to prove the theorem. So the theorem says that in dimension, I should give references. So this is by Jennifer Chase, Lincoln Chase, and Chuck Newman from 1985. They show that, so for D equals 2, the minimum spanning forest, let me say wired, but it doesn't matter, is a tree. Okay, so this we've seen is not automatic. There's something to prove there. And if you're interested in thinking more about this, here's a conjecture which has been open since then. You know, in So for d equals 1,000, this wired minimum spanning forest is not a tree. Okay. So there's a question about the definition here. Are edges only able to exist between the adjacent lattice points? Yes, that's what I mean when I say nearest neighbor bonds. So here's a picture of sort of Z2, if you like. These are the edges of Z2. Okay. That's the graph I'm going to be focusing on just for concreteness. Most everything I say sort of isn't particularly sensitive to the choice of lattice, as long as it's some nice regular underlying lattice that sort of is a reasonable discretization of d-dimensional Euclidean space. Does UIC fail in this case? I think in all of these cases there are unique infinite components, so I don't need to be writing the W if you prefer to leave it off. It's free or wired, it doesn't matter. Yeah. And just as a sort of tangent, for those who've thought about fractals a certain amount and intersections of fractals. So there's a sort of heuristic in a lot of study of sort of random fractals in space, which is that if you have kind of two objects which are like x dimensional and y dimensional, and sort of generic and reasonably independent, then in dimension bigger than x plus y, they shouldn't intersect. Okay, and in dimension less than x plus y, they should intersect. And this, can be used, formalized in lots of ways. It's sort of the underlying. If you have that in mind, then there's lots of guesses you can make about how random objects will behave, like Brownian motion intersections and things like that. That can be that are usually correct. And so there are sort of guesses about about the dimensionality of the trees of these random forests, which might give you a more precise guess about when two of these trees should have a positive probability of intersecting or of not intersecting, and would allow you to maybe lower this d equals 1,000 here to d equals 12 or something like that. But there's just some lack of tools for the time being to even tackle sort of ridiculously high dimensions. So if you have any ideas that can do this for d equals 1,000 or 1,000,000 or anything, that would certainly be very interesting. Okay, so I want to so we'll come back to this theorem later. But first I want to develop the connection between minimum spanning forest and percolation. I'd actually written in my notes to explicitly state the answer to that last question in the chat, that almost surely, ZD with IID uniform weights has unique infinite components. Okay, and in fact, we'll even, I can even state a more precise theorem if I give myself just a little bit of notation. Let me write. I guess I don't. This notation already exists, if you like. So ZD sub P, right? Because we were writing G sub T for the subgraph of G with weights at most T. So this is the subgraph of ZD with weights at most P. Okay, so then it's a theorem going back to 1989 that so in any dimension and for any value of P, almost surely so ZDP has at most one infinite connected component. I think there's only, as far as I know, there's only one proof of this available, which proceeds by analyzing like trifurcation points. Right. So continuing on, so I want to define a quantity which is analogous to the survival probability. So for Poisson bien-aimé trees, we define this theta of lambda, which was the probability the tree was infinite. So we want to do a similar thing for percolation. So in the Euclidean setting, I'm going to write theta, and I'll index it with the graph ZD of P for the probability that in this graph, the origin is connected to infinity. Okay, so by which I mean, you know, that the component of the the component containing the origin has infinitely many vertices. Okay, this is handy notation in general. Like it's convenient to write you know, U left right arrow GV to mean that U and V are in the same connected component of G, right? That the connected component of G containing U is the same as the connected component of G containing V, right? This says that there's a path between U and V in the graph G, and then this is sort of an extension of that notation to suggest that there's sort of an arbitrarily long path starting from the origin, right? So there's paths of all lengths. The component is infinite. Okay. Right. So that's the probability that there's percolation starting from the origin. That from the origin there are arbitrarily long paths, and then the critical probability is defined as. So this is the probability, the smallest probability for which this percolation probability is positive. So the smallest p such that theta of p is greater than 0. Okay. So here's a beautiful fact that I want to tell you the proof of due to Chuck Newman from, I think, 1995, early 90s anyway. I'll put the reference. This says that if we take the, so let's write T for the Prim tree built by Prim's algorithm starting from the origin. Or sorry, that's not quite. Let me start over. So we already have this notation TV, which is the Prim tree started from V, and now V is always going to be a lattice point. Okay. So what Newman proved is that if the probability that the origin is in this tree tends to 0 as the point gets as the starting vertex gets far away. So Euclidean distance, say. Then the percolation probability at the critical value is equal to 0. Okay, so it's worth commenting on this. Right up here we have so there are some values that you can just focus for the moment on the two-dimensional lattice that we see sitting here, right? If P is 1, then ZDP contains all the edges. So there's certainly an infinite component. It's just one component, it's infinite. When P is 0, there's no edges, there's no infinite component. And for intermediate P, there may or may not be an infinite component, right? So PC is saying you look at the smallest value where there's a positive chance that the origin is in an infinite component. And in fact, at that point, there'll be a unique infinite component. I mean, if there is an infinite component, it'll be unique. So we look at the smallest value where that has a positive chance of occurring, and then you can ask, at that value, is there actually a positive probability of seeing an infinite component or not, right? So if we graph theta of P, right? So if this is P and this is theta P, then the question is, the graph is 0 for a while until PC, and then it's increasing after PC, and there may or may not be a jump in a discontinuity in the graph at this value. Okay, so I think it's fair to say it's maybe the most famous open question in probability is whether or not this graph is continuous, so whether or not theta of PC is 0. Okay, and so this this theorem says that that you could prove that this graph is continuous just by showing that the origin is unlikely to be invaded by invasion percolation starting from far off. Okay. Is the statement clear? So there's a question in the chat about whether this theorem is about ZD or about transitive graphs. I'm just thinking about the proof. I think it requires I think we'll see in the proof that it uses unique infinite components. It does use unique infinite components, but maybe not more than that. Okay, so any other questions before I go on with the proof? Right, so the question is so the question in the chat is it true that it's not known whether this is equal to 0? That's correct in general. So when the dimension is 2, that is known. There are special features of planarity which can be exploited to show that in 2 dimensions, there's no percolation, there's no infinite component at the critical value. We also know the critical value is exactly half in that case. But in higher dimensions, so D at least 3, well D3, 4, 5, we don't know whether there's a jump here or not. And then in higher dimensions, it's known again using different techniques that there's no jump. Okay, so let me give you this proof. It's not fully self-contained. I'm going to use the Burton-Keene theorem that I stated up here, and I'm also going to use one other factor which some of you might not have seen, which is called the Fkg inequality, which basically says that when you have 2 events which are both increasing in some underlying randomness, and that so in our setting, turning on edges makes them more likely to occur, then those events are positively correlated. So I'll say that again when I actually use it. So let me. I'm going to, just for shorthand, write so CP for the component containing V in the graph ZDP. Okay, and now here's just a simple fact about Prim's algorithm. If the component containing vertex V is finite, then the whole component is contained in the Prim tree TV, right? And that's because Prim's algorithm will only explore an edge of weight greater than p if it has no options for edges that of weight at most p, right? So Prim will only use an edge of weight greater than p when no edge of weight at most p is available, right? But this component is, all the edges in this component have weight less than p. So Prim's algorithm started from V will first, add a spanning tree of CPV, and then it'll be forced to add some edge, leaving CPV to the rest of the graph. Okay. And so that says that if I ask about the probability that a given vertex U is in the tree TV, right, that's at least the probability that U is in the component of V at a given percolation value P. So that's true for all P less than the critical value. I should say, yeah, that's true for all P less than the critical value, right? Because if I look at P less than this critical value, then this component here is almost surely finite, right? This value was the smallest value where infinite components start to show up. Okay, so if P is less than that, then this component is finite. And then if this component is finite, that says that this event is more likely than this event. Okay, is that clear? Okay, right, and so that's another way of writing that is just that is the probability that U and V are connected in the graph ZDP, right? But this is now I can take a supremum over P less than PC, right? And get a better bound. So take the supremum in this bound. And that gives me the probability that that U is in TV is at least, so supremum P less than PC of the probability that U is in, well, let me write it as U is connected to V and ZDP, but that's just by continuity the same as the probability that that U is connected to V at the critical value. Okay, so that's a upper bound on the probability that two far off vertices are connected, given in terms of the Prim tree, right? It says that they're less likely to be connected at criticality than they are to be in one another's Prim trees. Okay, but now we can get a lower bound on this using Burton-Keene and the Fkg inequality. So this probability, one thing that guarantees that U and V are in the same component is if they're in the infinite component. So so this is at least the probability that they're both in the same component, and that component is infinite, right? Just because this is just one particular way for this to happen. Okay. But now, because Burton-Keene tells me that almost surely there are unique infinite components, this is the same as the probability that both components are infinite. let me write that as the probability that they're both infinite, right? Because Burton Keene tells me that if they're both infinite components, they must be the same component, because there's almost surely at most one infinite component. Okay, so this event and this event are the same up to a null event. That's what Burton Keene says, and so including or removing that null event doesn't change anything. Okay, so now here, these two events are increasing, right? If I add more edges to the graph, then it only makes things more likely to be infinite. Okay, so then the Fkg inequality tells me that increasing events are positively correlated. So this probability that both of these happen is at least the probability that one is infinite times the probability that the other is infinite. Okay, which is just what, well, using my previous notation, this is the probability that 0 is connected, or rather that u is connected to infinity or v is connected to infinity. But it doesn't matter what the vertex is, right? The lattice is completely translation invariant. So this is the same as really the probability that the origin is connected to infinity, which we had a name for, right? That was theta of PC. So here we just have theta of PC squared. Okay, so what have we what have we showed? We showed that for any u and v in the lattice, theta of PC squared is at most, chaining this inequality with this inequality, the probability that u is in TV, right? And so now I can just take u is equal to 0 and send v to infinity. To get that if the probability of the origin is in TV tends to 0, as v tends to infinity, then theta of PC must be equal to 0, because we have arbitrarily small upper bounds on it. Okay. So there's a question, there's a private question in the chat. Why can you take the limit as P to PC? I guess that relates to this supremum. I think it's just because the connectivity is like a countable union of over a countable union of paths. But I'd have to write it out carefully to be sure there's not a mistake there. I thought it was just continuity from below. But that's the sort of thinking that I'm very bad at doing on the fly. So so let me if there's an issue there, then I'll write a note after the lecture. Okay, so so that's potentially an approach to proving a major open conjecture in probability that no one has managed to use for 25 years. So it might not be as promising as it could sound at first glance. But I think it's an interesting observation regardless. So let's just conclude today with sort of a picture of what invasion percolation looks like generically on ZD. So this will be a little bit kind of heuristic and pictorial, but I think it's a nice way to wrap up the day. And then in tomorrow's lecture, we'll prove the two-dimensional theorem I mentioned about the forest being a tree. And then we'll move on to the mean field setting, start talking about what happens on the randomly weighted complete graph. Okay, so the picture of invasion percolation on ZD. So let's look at the thing I want to start by thinking about is the largest weight edge that's ever explored by the invasion percolation. Okay, so let's fix some vertex y and write P1 for the largest value P such that the component of y in the P percolated lattice in ZDP is finite. Okay, right? So that's, so here's, if I draw the component, here's y, and here's the component of y in the graph like G or ZD P1 minus, right? Just before P1, then we know that this component is spanned by edges of weight less than P1. So it'll get fully explored by Prim's algorithm. And then Prim's algorithm will be forced to add this edge, some edge of weight P1. Okay? We know that at P1, there's going to be an infinite connected component. So the component CP1 of y is infinite, right? And so that means that P1 is the largest weight of an edge explored by Prim from y, right? Or, you know, that means the picture is something like this. You know, over here we have the, that means that this vertex y is in the unique infinite component of ZD P1, but it isn't in the unique infinite component for any smaller value of P1, right? Oh, smaller value of P. So Prim's algorithm then will explore this component, it'll add this edge, and now it's sitting in an infinite connected component of this graph, so it'll spend all its time exploring edges over here, right? But now I can ask for, sort of like, I can take another step and ask, what's the next largest edge that it ever explores? So let's let P2 be the largest value of P such that, so let me call this far endpoint here y1, so if this edge is x1, y1, then so the largest value of P such that the component of y1 is finite, right? Well, we know that y is sitting in an infinite connected component at P1 minus. So there's infinite, so the largest weight, you know, so the largest value of P for which the CP component of y1 is finite will be smaller than P1, right? And so if we do Prim's algorithm starting from y1, which is really what Prim's algorithm starting from y does after it gets to y1, it explores over here, it crosses this edge, and then it starts exploring, right? Then it's going to explore some finite region, okay, of edges of weight less than P2. And then at some point it'll be forced to add an edge of weight exactly P2. You know, we could call that x2, y2. And then it'll find itself in an infinite connected component of the graph, of the percolated graph at parameter P2. Okay, so you know, y2, y1 is in the unique infinite component of ZD P2, and maybe it's bear saying, but not ZD P2 minus. Right, and so you can continue in this way. There's an infinite sequence of sort of decreasing values where you look at the largest edge weight ever explored, and then the largest edge weight explored after that, and so on and so forth, right? So if we then these values, they're getting smaller and smaller. They always have to be bigger than the critical value PC, because we're always finding infinite components at these values. Okay, so then it's clear that P1 is bigger than P2, and so on. It's bigger than no matter how long you go, you're going to stay bigger than the critical percolation probability. But in fact, it turns out, so this is another theorem of Chase and Newman, that so Pk converges almost surely to the critical probability, Pc. Okay. There's a question why P2 is less than P1. Basically because the percolation probability is known to be an increasing function beyond PC. Right. But so this, another way to put this, all of the edges that are explored between this edge and this edge have weight less than P2, right? So we explore a bunch of edges of weight less than P2, and then we get this edge of weight P2, which is bigger than the critical value. Then we'll explore a bunch of edges of weight less than P3 and add an edge P3, which is bigger than the critical value, and so on. So another way to say this, or at least a corollary of this, is that if we write WEN is the weight of the nth edge explored by Prim's algorithm, that this converges, well, the lim sup of WEN converges to the critical probability. Okay, so this is sort of quite a nice feature of Prim's algorithm over invasion percolation, which is that you don't tell the process the critical value, but somehow it in a sense zooms in on the critical value for percolation of its own accord. Okay, so this in some sense justifies the use of the name percolation for it. It has this sort of natural and close connection with critical percolation, and this also gets, the jargon for this is self-organized criticality. Okay, it finds the critical value without being told. Okay, so I think that's a good spot to wrap up for today. Sorry I wasn't able to quickly answer the question about taking the supremum over P less than PC. I'll think more about that. And have a good weekend, everybody. See you Monday.